Hi everyone, this is my solution to problem B3 of the William Lowell Putnam Mathematical Competitions, the 75th competition that was held on December the 6th, 2014. So here's the problem, B3. I presented the solution in our colloquium series in the Department of Mathematics, Armstrong State University. And I really had fun with thinking about this problem, and it's not essentially the shortest solution, but it has interesting ideas in it, and I had fun with it, so I'm presenting it here. Well, here, let me read the statement of the problem. A be an m by n matrix with rational entries. Suppose that there are at least m plus n distinct prime numbers among the absolute values of the entries of A. Show that the rank of A is at least 2. So it's absolute values of the entries of A. So this is not just a prime number, it could be negated prime number such as -3, -5, things like that. First we're going to think about the meaning of the rank of a matrix. That's the one thing that we're going to do first. So I think the rank is well explained, and the whole terminology is well motivated in this context. It's a map from n-dimensional vector space to m-dimensional vector space given by this matrix multiplication. Then the rank of that matrix, of that map, or that map is defined as the dimension of the image, or it's also called the range of T. So here's an example. This matrix participation really explains well what's going on. What is this map doing to this input n-dimensional matrix? Here is a 3 by 3, so n is 3 and m is also 3. So this is input, each entries of one vector that is coming from Q3. And what is this matrix doing is, if it is not the way you understand the matrix multiplication, you'll easily verify it's the same thing. The advantage of this one is showing immediately how the image looks like the first column vector is multiplied by the scalar C1, and second column vector and third column vector multiplied by these scalars. So input vector is stripped apart and serves as a scalar multiple of the column vector. So the size in here is supposed to be size of the output vector. So it's a linear combination of these three column vectors. So that's what's going on. So in general, if you have m, it's this size here, by n matrix, then as you multiply, you'll be computing a linear combination of this column vector and the last column vector with scalar multiple. So the dimension of the range, so this will be the range. Everything you get out of this map looks like this linear combination. The dimension of this one will be the rank of a matrix. So because of that, range itself is simply the span of those column vectors, and the rank will be the dimension of the span of the column vector. Often in the first year linear algebra course is introduced as a column space. So the rank is a dimension of the column space. So I recorded that important kind of interpretation of this rank thing. And let's think about, well, the problem is concerning rank at least 2, so let's start with the meaning of rank 0. If it is a span, and how can you get a dimension 0 that all the vectors should be 0? So it's not a very interesting case. So if we have some distinct prime numbers in here, we know this is not going to be the case. So meaningful case to think about is rank being 1. So that means the linear span of this column vector is spanned by one single vector. That might be one of these vectors, might not be, but it's definitely sitting inside the linear combinations of these n vectors and should be non-zero. So that its rank is precisely 1. And here I'm trying to argue that if everything is generated by this little w, and you can rearrange it so that one of the thing will eventually also generate the same thing. So if you look at it here, what I'm trying to say is that each of these AKW, whose W is a generator, can be rearranged like that so that that AKW is also a scalar multiple of AJW. Simply by canceling this one, you can easily verify it, but AJW was one of this vector in here. As long as this AJ is non-zero, and we have some of those vector, AJ must be non-zero somewhere in here. So if you choose that vector, and if you multiply, you get AKW. So everything here, which is written like this, is also generated by AJW, and we can even generate that W with AJW, things like that. So I guess I'm trying to claim that span is actually generated by one of the vector AJW, so that it's, for example, WJ. I think that part is simple. And this part in here, I'm trying to explain a little bit more about now the context of the problem, not the rank itself, that we understand the rank in here. So it's about, the conclusion is the rank of A is at least 2. I want to look at this 1 by 3 sides. Here's a number of rows 1 and columns 3. If you look at this one, think about column vector space. The column vector, this is a column vector with dimension 1, and it's going into the dimension 1 space. Therefore, we're not going to get rank greater than or equal to 2. It's at most 1. So that statement is different. The rank is always going to be 2. But we didn't take that into take the following into account. At least there's m plus n distinct prime numbers involved in here. So if you look at here, 1, 3. So that 1, 3 makes 4, but only 3 matrices, entries in here. So it's not satisfying. So let's look at next idea. Is m plus n is a number of distinct primes we have. We want to put it into the size of m by n matrix. So of course, if it goes in there, this must be less than or equal to m times n. So if we simply divide both sides by mn, then we arrive in this to this equation, where since mn are integers, positive integers, and to obtain that inequality, mn must be greater than or equal to 2. If any of these is 1, then you can see that exceeds 1. So the least case that we should consider is at least 2 by 2, and that's the smallest case we can consider. Another thing is this absolute values of the entries. So usually when we say prime number, that's a positive integer, but in the theory of rings, prime element is not really distinguished. You can multiply any unit, multiplicative unit of the ring. Here in the integer, there's a positive 1 and negative 1, and those are the only multiplicative unit. There's something that has multiplicative inverse. So we will treat that negative 3 and negative 11, those as a prime element, or simply say prime, so that I don't have to worry about this absolute values thing. Right, here's our base case 2 by 2. M plus n, well, 2 by 2 is 2, is m plus n is 4. So there are 4 distinct primes and 2 by 2. So everything in the entry is a prime number. So we want to show the rank is not 0, like I said. It will never be 0 because there is a non-zero element in there. So let's suppose its rank is 1 if this goes wrong, and then we show at least 2. So here's our matrix, and everything is a prime number, and we suppose its rank is 1. So the other column vector is generated by scalar multiple of the other one. So if you take the quotient, or if you solve for k, we arrive at here, k is b over a, k is d over c. So they are common like this. If you write it and knowing that these two quotient of fractions are in the lowest form already, and these are all prime numbers. But by, I guess, fundamental theorem of arithmetic, and these should appear exactly the same. So B must be D, A must be C. There's no other way to write fraction and lowest term. So that concludes the proof that this rank being 1 and these 4 things being distinct prime numbers is a contradiction. So these are linearly independent vector. That's how I looked at this problem. So I had to go to the larger cases, but that gave me a very good idea about what to think, what to do with the problem. So it was my goal, if you have in general m by n matrix, and I thought if we have m plus n distinct prime numbers, and I wanted to argue there exists this 4 prime number within that m plus n distinct prime number, such that those 4 prime number form this square position, not over here and like that, just 1, 2 of them in a row like this, lined up in a column like this. If I find these 4 distinct primes, then I realize I can argue exactly the same way with a 2 by 2. If I look at this 2 by 2 matrix of this ABCD, I can show there is no scalar multiple that reaches from here to there. And if you think about it, you can easily extend that argument to the entire column. So if this is ABCD is in linear independence, that extends to linear independence of 2 columns they belong to. Let's try to write that part in here to make it clearer. So how can I argue something like that? First thing that came to my mind was the pigeonhole principle, and I tried that, and I couldn't get any nice setup. The pigeonhole principle worked. So the next thing I could think of was this mathematical induction. So kind of try to reduce the size, and so let's think about it here. We're given a matrix. I want to kind of remove the rows and column and things like that, and get down to the smaller size of a matrix, and have enough number of primes still there, and wanted to argue that there exists the primes for such prime. So that was my first attempt. It didn't work, and I had difficulty, so I changed my mathematical induction statement to, let's forget about this existence of 4 primes, to show exactly what the rank of 2 greater than or equal to 2, by again removing rows and column and things like that. So in that idea, my induction the parameter had to be this m plus n. Okay, I hope this will be explained better as we look at the idea of the induction. So I pursued it, but I found this counterexample in that process which defies the existence of 4 primes like this. So this is 3 by 3 case, and these dots represent distinct primes. Even if there is a prime out other things in other places, we ignore that part. We just focus on these 6 dots which are distinct primes. So I lined it like this so that it has 3 plus 3, 6 distinct prime, this distributed above here. And if you try to find these 4 prime numbers, they're lined up like this, and you can easily conclude that it's not possible. There's fairly small number of things to check, and it's not possible. So that statement I showed you earlier is actually, I didn't just fail it, it is not true. This statement is not just simply true. But that case actually gave me an interesting case, and realized I need to focus on this special shape more. So here's the rearranged part, and next time rearrange it into this one. These dots are again distinct primes, and if you look at this case also, you cannot find any square like this ABCD lined up like this. And this turns out to be turns out to be my attempt toward to induction process is a problem. So induction process, you remove, my idea of induction process, you remove a row and a column. By doing that, you might lose some of the distinct prime numbers in here. If you happen to have one, for example, if you're looking at here, rows and columns are about to remove in this induction attempt, and if you can find just one row or column that contains just one prime, then I'm losing one distinct number of primes and reducing the size of the matrix by 1. So it's kind of putting exactly into the induction hypothesis. But if you look at it here, the problem is that rows and column everywhere, they're exactly 2 distinct primes. So by removing it, you're losing too many distinct primes, and that was, this case here became a serious problem in my induction attempt. So after I solved the problem and I realized that it better be rearranged like this, so this is also have the same property. Every row and every column have exactly 2 distinct prime numbers, and this one I decided to arrange it like this so that I can show you the kind of argument more consistent way. The pattern, it seems clearer to me. So because of that thing that I just showed you became the hardest case, I decided to focus on that one first. Of course, I solved it later, but in terms of presentation in here, I think it's clearer in terms of logic that I showed you this proof clearly first. So that case was always coming from that M square matrix M by M, and P is the set of distinct 2M primes that was M plus N before, now it's 2M primes appearing in A. And this is the condition: each column and row contains exactly 2 distinct primes of P, just like the picture I showed you. Then I just take this separate special case and show the rank has to be at least 2. So let's take care of this case first. And this is exactly the case that attempted my induction reduction process in my mathematical induction. Alright, this was a fun part. If you have a matrix, like a square matrix in here, and row and column swaps do not change the rank. It's just not hard to understand. So let's start with column swap. Remember, the rank was a dimension of a column space. So you list the columns into the span formulation, but the order of this thing doesn't matter. How you order your basis dimension doesn't change. Therefore, it's easy to understand the rank doesn't change if you swap the columns. So here I'm actually showing you that thing. So this is the linear combination. If I order, I think it's easy to see, so I'll skip. Right, kernel is also easily understood, but it needs more explanation. So here's a 3 by 3 matrix. The kernel is the set of all vectors that, when you multiply this matrix, become 0. But we really learned this whole setting in terms of equation like this in the beginning of first year linear algebra. Row swap will be just rearranging this equation. For example, if I swap these 2 rows, and you're going to end up at this matrix. If you actually expand this one, you end up at this system of equation. This individual equation, however you solve it, in what order, the solution space is the same. So this is also summarized as a kernel of this matrix, or null space of this matrix, is invariant if you do the row reduction, elementary row reduction, which includes this swapping in here. Right? Therefore, this kernel doesn't change, or null space. Let's think about this well-known theorem. M is the dimension of this map going from m-dimensional space, here m-dimensional space, to another m-dimensional space. The dimension of the domain is the dimension of the null space plus dimension of the rank. As we swap, this doesn't change. this doesn't change, not even the dimension, but the kernel itself doesn't change. Therefore, the rank doesn't change either. Alright, by doing that, row swapping, we keep this rank of a matrix. So we're doing the induction on the number of primes. In this case, we have 2m. So we suppose it has rank 1. And doing this row swapping and column swapping, I'm going to rearrange this special property right here, 2 at each column and row, into the shape that I showed you. So look at the first column, there are 2 distinct primes. Then you can do row swap. You can put that one up there, but entire row goes up there. And the second row like that. So if you just look at the row, they lined up like this, and the rank of this matrix is still 1. So you look at the second row and find another distinct prime in that row, and you do the column swap to move it over here. Next question you have to ask, now you look at the second column, and there must be another prime. It's either above here or below there. So for example, if it is above there, and this itself forms a square matrix with a sufficient number of primes, 2 by 2, and there are 4 primes. So it falls into the induction hypothesis that is the smaller size. These 2 things have rank at least 2. This rank at least 2 actually extends to rank at least 2 of these 2 columns. Therefore, rank at least to the entire thing. So that's not the case. We assume it's rank 1. So it must be down there, not in here, below that, outside the square matrix. So by row swapping, you put it up there. And this row here has only 1 right now discovered, distinct prime found. So you look at find another one. If that's over here, that makes no sense. It's just 3 primes lined up here, so they must be outside. So that's the one thing that you have to be careful about. You move it over here by column swap. Then you look at the column again, and you think about whether the prime's up here or down there. Because of this condition, we can't put it here. It must be over here. So let's look at that position there, and noting that in general, the way it goes is that I don't know why I put there, but let me just explain it. Here, there was 1 prime, that's a 3 by 3 now. Then we have, I remember now, 2 times 3 is 5. There's only 5 primes there. So if I put 1 more prime there, that falls into another induction hypothesis. So inside we have enough number of primes for 3 by 3. Therefore, 2 of them, as soon as we put it in there, 2 of them is linearly independent. So that extends the entire matrix. So still violating this one. So we have to put it down here. So at this point, I just like to claim that if I keep doing that, you will arrive in this situation. Or you can't be over here anywhere because there's always 2 of them there, so you have to be shoved it out in here. So if you start with this condition, by row swapping, you can always rearrange it like this, keeping your rank the same as the original one. And if you think about the last dot, that it should appear in this column, and there's no choice, it must be all the way up there. That's the only possibility. So I claim that it's going to be rearranged like this. So here, this real little recursive part, this P1 and Q1 as a prime, P2, Q2 lined up like this in the second column, go all the way down to the last column, but last column has a slightly different shape. So these are all distinct primes, and I'm going to do something about rest of the element in the first column. Basic idea is that if this is rank 1, then there's distinct prime. By scalar multiplying to the first column vector, I can reach this guy, that guy, all the way to the end. So this shape allows to consistently, actually we can do that, but by the time we reach here, if you pay attention what happened to Q6, something goes, contradiction you can pull out. So, once you look at this first two, that's the square box. Let me put it like here, that's the thing to pay attention right now. So this one says the following, that because this is a scalar multiple, the quotient of this one, Q1 divided by P2, A3 divided by Q2, so I put A3 in the numerator so that you can easily see the algebra. So if you solve for A3, then that one, because the scalar multiple, you can fill in this A3 in here with these distinct primes. And I'm going to do the same thing for the rest of the part. Let's see what I have written down. So let me convince you. For example, if you look at this column vector and that column vector, you can see this is given P4 and Q4. And suppose we figured out A4 and we're going for A5, then you're going to put into that equation. Let's see if I wrote it correctly. And so let me look at this. It's A5 divided by Q4. This is A5 divided by Q4. That one is going actually the denominator in here, like that. And A4 divided by P4. I hope this general equation is convincing enough by looking at these two pair like this. So you're going to be always like this, and you can be rearrange. We can rearrange it like this. So once you do that, it clearly shows you how to compute AK plus 1 using AK, and these other ingredients are these prime numbers we found at the beginning of the problem. So recursively, you're starting with this A3. Recursively, find all that. The rest of the part is me showing you that's how this recursive relation unfolds. It's really just keep multiplying this number. So it's not hard to show this AM, which is the last entry in here. And if you keep unfolding, it looks like this. Keep multiplying this QK and PK in terms of QK and PK diagonally like this, Q2, P2, and so on. So P QM minus 1 PM, although it's kind of slided here, it's, you know, its alignment is strange, but I think you will verify it correctly. So that's AM right there. Now it's time to, actually we got that AM by comparing this first column and the second to the last. So if you compare that first and the last, what we're going to get is that PM divided by AM and QM divided by P1. They should be the same as scalar multiple. So now if you solve for QM, which is new prime that just entered, and that's why I am isolating that, then it's PM, P1 divided by AM, and AM showed all this shape, and this is lowest term. Everything is a distinct prime numbers, and here we added PM. You know, there's no sign of QM in here. So fundamental theorem of arithmetic again says that this should be happening. So rank 1 is not true. Rank must be 2, at least 2. Right, this was the most important case, and I had fun with this row swapping and the thing, so that's what I want to mainly enjoyed. So that case is under control now. So we're going back to the original problem, m times n matrix. We have m plus n distinct prime numbers. Induction is done on the number of distinct primes. So we're going to strip off rows in a column and get down to the smaller size of a matrix and potentially smaller number of distinct prime numbers, and hope we can control that. All right, it's the same setup, matrix, and m plus n distinct prime number A. Let me understand this induction process is not set of the square. Okay, so the K is that this is the thing. The K is a minimum number of primes appearing in a row or in a column. So you look at all the rows and all the columns. look for minimum number of primes that is appearing in there. Of course, because of the reduction process, the idea is removing the rows in a column, and we want to keep that under control, not removing too many, so that we can have this right number of distinct primes that's still sitting in that smaller size of primes. So here's what I discovered. It wasn't that too bad. The minimum number should be less than or equal to 2. And even more surprisingly, if it is 2, then that matrix must be a square matrix and satisfy the condition that we just looked at in the claim 1, which is each one has 2 in each column and row has exactly 2 primes of P. Alright? So mainly, we've done that k equals 2k, so it's mainly about k equals 1 case. K equals 1 case, by removing that row, we only lose 1 prime. So that's the whole idea in here. Alright, this I had to divide like that. I think it's sufficient enough. Let's look at the case where m is this size, is smaller than n. And I counted a number of primes in each column. So in this case, I have 4 primes lined up in that particular column in there. And next equation is that this is the minimum number anyway, so ck is always greater than or equal to that little k. So if you sum up, left-hand side is just multiples of k, n times k. Right-hand side is adding up all the primes we have, which is n plus n. It might have more primes, but it is primes in this p here. That's what we care about. So nk, this whole thing is m plus n. So k, if you divide both sides, is m divided by n plus 1. So that m is smaller than n, so it's strictly less than 2. So k must be 1 or 0. So that proves this case. Let's look at m greater than n. I realize this time we're going to count rows. If you look at rows, there is 4 primes, for example, and the k is still the minimum appearing across that. So k is less than or equal to the number of primes in that kth row, and we sum up, arrive in exactly the same equation. And when we divide it this time, I was able to put this m in the denominator, so I can still show that it's less than 2. M is greater than n. Well, that was a nice trick, that counting in a different way, different directions. When m equals n, ck is the number of primes. I'm looking at columns first, but eventually count the rows as well. Is column. And this is a slightly different argument because I cannot get that strict inequality. I have to look in a little more detail. If k is the minimum, if there is one of the columns there that it has more than this minimum, some j, not all of them, then this is true, k is less than or equal to ck, but when you add them up, there's at least one number in here that is actually bigger. So this inequality becomes a strict inequality when you sum it up because of this information. See? Then you do that again, is n times k, and this time is both the same, so it's n plus n, so you can see k is strictly less than 2. If there is something that's bigger, it still has to be smaller. So this argument goes, wait a second, so what is it saying? It's k is, so the conclusion is that if k is equal to ck, there is no column that is more than this minimum number, then of course k equals 2. Everything is 2 in there. And if you do this argument along with the rows, and that's exactly the same, so I wouldn't go through. But the earlier case was k less than 2, and this is k equals 2, so that's the only case that is going to occur. When is k equals 2? If you look at all the cases, only time the k equals 2 is this case. Every rows and column is exactly equal to the minimum number, which happened to be 2, and that satisfies the context of claim 1. Therefore, I prove this statement. So I'm showing the clam 1 again. It's a separate statement. It's more difficult case. The square matrix, each column and row has exactly precisely 2 primes, then rank is at least 2. So come back to this original problem. Finally, just laying out the entire induction for that original problem. So the case, lowest case L equals 4 is proved at the very beginning of this video. So suppose the statement is true for all the matrices of this L greater than or equal to 4. Should be greater than or equal to 4. I don't know why. I hope I catch that. Greater than or equal to 4. So that induction starts from right here. Right? Alright. Let's see what happened. And it's the same setup. P is the a set of m plus n distinct primes, and k is the minimum number. Alright, with k0, the minimum, there is a row that does not have this primes at all, and we're going to remove that row or column. For example, if this is matrix, this is the one that does not contain our primes at all, then I can remove that. By removing it, the size goes down a little bit. So since size go down, our only thing we require is m plus n minus 1 primes, but we still have m plus n primes here. So it still satisfies the hypothesis. So there are 2 columns such that they're linearly independent, and since there are at least 2 rows in here, we still have 1 row left, right? M is greater than or equal to 2, n is greater than or equal to 2. So induction hypothesis apply here. Columns as well. So a prime has reduced size after you remove it, contains m plus n primes, which is good enough. M plus n minus 1 is what we needed. Let's look at case 1. And if you remove it here, just like we did it before, then size goes down, but also we lose 1 prime because it contained one of the primes. But that's just right, m plus n minus 1, and that's the size of this matrix A prime. So for A prime, L is this number, and we have that primes in here. Well, k equals 2 is the case. If k equals 2, it was the case that A is a square matrix satisfying this condition in here. 2 distinct primes, each column and row. Therefore, I think I proved it. K equals 2. It adds this already independent statement for that special case. So to wrap up, this was the statement. A is being m times n matrix with rational entries. Suppose that there are at least m plus n distinct prime numbers among the absolute values of the entries of A. Show that the rank of A is at least 2. We looked at this k equals 2 in the special case first, and for the other case, k equals 0 and 1, induction applies nicely. Well, it didn't go like that at the beginning, and I'm showing you here lots of sketches I went through to figure out how this thing is lined up and other possibilities and things like that. Thank you very much.